Okay, I can recall this poor woman who was beaten up on the street long time ago even, but I vividly remember that. But I don't remember, for example, my cousin being beaten up by some, guy on the street, because that happened maybe too often that I sort of take it as a normal thing, so I didn't even recall it that often. So I thought, elderly person is more, easier to get this kind of a violent crime. Okay? And the second one is easily imagined events are not necessarily more probable. Okay, so this is in a study where they ask people in the beginning of a semester, they ask students whether to imagine what's gonna be the result of this course. What's your grade? What's your grade at the end of this course? And most people report either fail or high pass. Okay, but in reality, not that many people fail the course, but also not that many people got a high pass. Because based on usually the teacher curve the whole grade, right? So by curve, it means that the mean is gonna be somewhere maybe around 70, 80. And so most people are around that number. But most people wouldn't predict that in the beginning of the semester. Because because fail is a memorable thing, right? And high pass is also a memorable thing. Easily imagined thing. I can easily imagine, I have a high pass, or I have a fail score, or maybe I ask you to imagine your future life in your 30 something, okay, or your 40 something. I guess most people wouldn't imagine they are having a so-called ordinary life, right? Because it's really hard to imagine what is ordinary life. You sort of either imagine you're doing not so good because you imagine that the world is gonna be really bad and something like that, or you're gonna imagine, I'm gonna be so successful because I'm gonna start up this new company and gonna earn a lot of money, or I'm gonna invest a lot in the stock market, I'm gonna be very successful, something like that. So it's easily for you to imagine that, but maybe harder for you to imagine you are having a normal life. But what's normal? It's really hard to define in the beginning. The third one is called illusory correlation. Okay, so we all know what's correlation, right? Correlation means two things are bound together, sort of not independent of each other. Okay, for example, your height is correlated with your weight. Okay, so you're taller. On average, your weight is larger, heavier. Sorry, but sometimes these correlations are only illusionary. So you're sort of imagining them. Okay, for example, if you are, for example, I forgot which country this is, but they ask people to think about a foreign cargo or foreign import of a good or a component in a factory. I forgot exactly which one, but basically something this company imported from the outside world, outside their country, and because they usually imagine that the goods from that company has a worse quality, so they imagine that everything from that company, from that country, gonna be a bad product. Okay, but that could be true even in general, but for a particular good that might be wrong. Okay, maybe that product from that country is actually has better quality, right? So you don't know exactly that. Okay. By the way, So at least 2 of you are sitting in the wrong position. Like I said before, you need to sit in the exact position that you were sitting. So in front of you, there cannot be a person. So so either one of you need to change the seat. So I think it's you that's sitting in the wrong position. Yeah, because in front of you there's a person, right? Immediately in front of you there's a person, so you cannot sit there. Your seat must be somewhere else. Yeah, you can sit just next to it. That will be fine. Yeah. Yeah. So or maybe like I guess in Taiwan, we usually imagine that import from maybe Japan has higher quality. So maybe when you're talking to someone, they said this is imported from Japan, you will assume that they have high quality. But in reality, that might not be true for a particular good. Okay, so the probability that a good has high quality or not may be independent of that, and you might be using a heuristic to deal with this kind of probability measure. Okay, so the second one is the representativeness heuristic. So this is used when you judge the probability that an object or a person belongs to a particular category, okay, or an event originates from a particular process. So it means it's an element coming from a set. Okay, the idea is that. So what is the probability that a particular element, for example, what is the probability that someone say Peter is in our class, or Peter is a accountant, or Peter is a student? What's the probability of that? So Peter is an element, and accountant or student is a group of people, a set. Okay, so in this case, a lot of time the assessed probability is based on the extent to which the object or person or event appear to be representative of that category or process. Okay, what that means. So this is kind of a famous study. So you ask people, for example, you told people that, for example, you said that this is everybody, and maybe among these people, 30% are lawyer. I will just do this. 30% are lawyer, and 70% are doctor. Okay, and then you give a description of a person. For example, this person in this party, he's wearing a suit. He's what else could be attribute of a lawyer that people usually think of? He's talking too much. Okay, yeah, okay, whatever. So talking too much, wearing a suit, a list of them, and you ask people what is the probability that in this group of people, he's one of the person in this group of people. What is the probability that this person is a lawyer? Okay, and because I said it's only 30% on average this person is a lawyer, but you have some updated information, right? It's more likely, you think there's more likely this person is a lawyer. So you maybe give an assessment of 50%. Okay, but suppose I give you another, so this is another group of subjects seeing a different condition, where this time it is 30% doctor and 70% lawyer. Okay, and you ask exactly the same question. So this person is, taking a suitcase and wearing suit and talking a lot, talking too much. Then on average, people also give you an assessment around 50%. Okay. And this must be wrong, because that means people are not adjustment based on the so-called base frequency. This number, 70%, 30%, these are called base frequency. So you should be updating based on that. So if you answer 50 here, you should be answer something around 80 or something like that here. Okay, but actually people are not updating based on that information. They were only thinking about this description of lawyer. So if you're saying he's wearing a white coat, white jacket, white coat, then you will think that this person is more likely to be a doctor with a fixed probability. You are imagine something that's representative of this group of people, doctor or lawyer. Okay, so that's what it means by ignoring base rate frequency. Also, this is also a very famous thing. So, let me ask you this. So, if you are flipping a coin for many, many times, a fair coin independently many times, and H means head, T means tail. Okay, so if you see H, tail, head, and another sequence that's H, tail, 1, 2, 3, 4, 5, 6. Okay, H, tail. This is sequence 1, this is sequence 2. Who thinks sequence 1 is more likely to be random? Who thinks sequence 2 is more likely to be random? Okay, who think they are equally likely to be random? Yeah, okay, so actually you two are correct. So, but most people think the previous one, the first one, the sequence 1 are more likely to be random. They expect to see something sort of look random. But actually the probability that these two sequences are random are exactly equal because they are both half to the power of 6. Exactly that probability. Okay? This is different from, by the way, you say that out of 100 times, you see 90 head. And this, out of 100 times, you see 10 head. 50 head. 56, okay, 56 head. Which one is more likely to be using a fair coin? Then it's true that this one is more likely to be a fair coin. Okay, because if you use a Bayesian updating. Here, they are both, the probability are both this. This is because the exact sequence is given. And these exact sequence happen with exactly that probability. Okay? Oh, and this one is easily demonstrated using a roller wheel. So if you go to a casino, you see this, right? And do everybody know how to play this? No? Okay, so basically, there is this wheel, and it has like 0, 00, and 1 to 36. So there are totally 38 what's they called? Bin or something. And then the dealer will just throw a ball into this wheel. The wheel go into it and it will stop at one of these slots. And if the slot is at, say, 36, then people who put bet on 36 will win. People who put bet on the red will win. People put bet on the this means even will win, something like that. So suppose we don't care about this part yet, we just care about this number here. So if you see a sequence of a lot of so you see a sequence of 36, 36, 18, 18, and 18, and then maybe 20. People would think that the 36 is less likely to show up in the next round because 36 already show up twice. And 18 is even less likely to show up in the next round. But in fact, they are all 1/38 probability. unless the dealer is cheating. Okay, but if it is a fair wheel, then it's actually all even probability. But you do see exact same number to show up more often than 1/38 in a short sequence. Okay, but if you observe a long sequence, it's all around the same number. And conditional on the sequence doesn't help you predicting the next. Okay, unless you believe in some kind of a outside source of manipulation. Okay. The last one is this regression to the mean. What is regression to the mean? So, this is actually contrary to a lot of the belief that people have. So, if you have a parent, you have two parents, that one of them, for example, or two of them are both taller than average in their generation, okay? Then much taller than the average generation, for example. Then it is more likely that you will be shorter than the average generation. Because it is unlikely, for example, also, I know people are confused because there's some kind of sort of gene involved, right? But gene actually have this property of regression to the mean. So if your dad and your parent just a little bit over the average, then you're sort of also have the same probability of being taller than the average or shorter than the average. But your parents actually is much, much taller than, unless he's carrying a gene that, for example, is a disease or something, directly, like correlationally, causally cause you to be growing tall. If that's the case, that's another thing. But if it is just the normal, like nature environment, then you're more likely to be shorter because the whole trend is converging regression to the mean number. Okay. Another example is most people who are very famous athletes, their children are actually less likely to be that good. They're usually not that good as a sports player. Okay, so example like Ken Griffey Jr. is actually better than his dad as a baseball player. It's actually a very rare event. That's actually why people remember it. Most people, even if their parents and them are playing the same sports professionally, their kids, if their parents are very good, they're actually not that good. That's the usual case.
Usually not that good or not that good compared to their parents?
Compared to the mean, their mean. That the same level of mean. Yeah. So another example is very famously used in this, it's called the Sports Illustrated event, phenomena. Okay, I'll call it phenomena. So, do you guys know this magazine called Sports Illustrated? No? So this is a very famous sports magazine in the US. Okay. I picked this because they usually are not having like men's on the front. It's actually girls. Okay, so with bikini, something like that. Okay. But they do put, because they're a sports magazine, right? So they do put MVP players in all kinds of different sports on the magazine front. In this case, there are two Yankee players, okay? And there must be, this is, actually I'm not watching MLB that year. This is baseball 2018. So this must be two Yankee players who play really good in that year. And this famous Sports Illustrated phenomenon is that people usually say that, if you show up in the magazine front page, the next year you're gonna perform badly. So you better not go to shoot these front page. Yes?
It's just superstitions, like it's not, I don't know, it's like,
But
it's just, it's not like it was scientists
So I'm saying that it's actually not completely that. Okay, the reason why is this regression to the mean. So I was talking about your parents and you. These are two different people. But if on the same people, this is like if you're batting really well above your average ability this year, you're batting even above your average ability this year, you are more likely to be the MVP this year, right? So, or conversely, if you are the MVP player this year, it must be you're performing way above your own average ability. You're sort of lucky, or you know what I'm saying? Yeah. Then the next year, it's less likely that you're as lucky as the previous year. So you're more like conversion to the mean. Your own mean, okay, your own average ability. So it's more likely that you're performing actually lower than your average this year to sort of counterbalance out. It's more likely that will happen. So that's why you will actually observe that phenomenon, but not because superstition or something like that. Actually, this is the last one. So this is a very famous example. It's even has its own name called Linda problem. So Linda is a 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. And then the question was asked like this: which is more probable? First one is Linda is a bank teller. Second one is Linda is a bank teller and is active in the feminist movement. Who think the first one is more probable? Okay, 1, 2. Who think the second one is more probable? 4, 5. Okay, so 2 and 5. But okay, so this is actually the usual research finding. Okay, more people think that second one is more probable. But if you see this as condition A, this is also condition A, or event A. And active in feminist movement is event B. So the probability that the second is true is P, A intersect with B. And the first one, this is P, probability of A, right? And by definition, you have these relation. PA must be greater or equal to PA intersect with B. Right? Yes.
But because they're in both, don't they cancel each other and be more focused on the feminist part?
No, that's not true. Mathematically not true. Yeah.
The way the question is put, like basically, because you have bank teller in both, you don't really pay attention to the bank teller part, but more about is she or is she not the feminist?
No, that's not the way the question was asked. The question was asked exactly which one is more probable, right? Yeah, if you think he's not less likely to be a bank teller, then he's even less likely to be a bank teller and also active in feminist movement, right? You were saying that PB must be high. You're saying PB is high, right?
No, I'm just saying that in this kind of question, like you kind of tend to not pay attention to the bank teller part anymore, but more about the only remaining part, which is different. Yeah,
that's exactly the heuristic here. You're using a heuristic here, but that's actually not a good heuristic because the fact is, by definition, PA is greater than or equal to PA intersect with B. Yeah. Okay. Question so far? No? Okay. And the last one is called anchoring and adjustment. So when people are estimating a probability, people usually start from an initial value, or this is called anchor. This initial value is anchor. And you adjust from it to get their final estimate. Okay, I actually showed this in one of the first experiment that we run in this class. I asked you whether the Mississippi River is longer than some number or not in the first question. And it's longer than X miles in the first question. But this X has two different groups. In one group, I use a relatively small number. In another group, I use a relatively large number. So maybe for the first group, I say whether Mississippi River is longer than 300 miles. And the second question, I ask you whether Mississippi River is longer than 50,000 miles. Okay, something like that. And then the second question I ask you, in both groups, I ask you to estimate the length of Mississippi River. And your answer shouldn't be depends on which group you are in, right? You might be not that sure about what's the length of Mississippi River, but so does everyone else in the classroom, okay? So between these two groups, there shouldn't be a large difference. But we did see that there's a large difference, if you remember. And the reason why is that people see the first question and they were adjusting, even if they think that is not 50,000 miles, the Mississippi is not that long, it's less than 50,000 miles, it will still adjust from that 50,000 miles and down. So you will only adjust to something like 30,000 miles, something like that. You're not gonna go all the way down. On the other hand, people who see the question of 300 miles in the first part, they will adjust from 300 miles. And even if they think, oh, come on, 300 miles is way below. So you adjust up, going up. But you only say something like 3,000. That would be, you say 10, that's already 10 times. Right? So you think that's really large. Okay. And this you might think, I'm sort of tricking you, right? I asked you about the length, whether to judge about the length in the first part. But there's another very famous experiment by Kahneman and Tversky. They simply ask you to sort of roll a wheel, like a fortune wheel, before the experiment starts. Everybody roll their own wheel. The wheel will give you a number from, say, 0 to 100. And you know that wheel is completely random, right? You come into lab, I tell you that this wheel is random. You sort of spin the wheel and get a number, say, so I say 36. You know this is a random number. And then, in the second part of the experiment, I ask you to estimate a length of something, or anything. I ask you to estimate a number that you're not that sure. Somehow, people who get a large number in the first part, say who get like a 90 or 80, will on average estimate a higher number than those people who get a low number in the first part. You know it's completely random. You don't know about other people's choice, but somehow you are using the number that you're getting from this random wheel as a anchor. Okay? So, it's really weird. And this one is overestimating the probability of conjunctive events. So, you guys know what is this, right? You should have saw this in like junior high school or something, high school. So this is an electric circulate, right? So basically, this is where the voltage go. Where the voltage go this way. So each one of these is I forgot the English term? Do people know what's that?
Generator?
The what? I know 中文 in Chinese is called 电阻, but I don't know what's that called in English. Or you should know that in your own language, right? I mean, you know what I'm talking about, right? So basically if this fail, the electric cannot go past, right? If one of the in this design, if one of these fail, the electric cannot go through, right? And suppose the probability that the wheel actually can work is 90%. And there are totally 7 of these. Each one has an independently 90% of success. Then don't use math, use your intuition. What's the probability that you think this whole circular can work? What's your intuition? Say, who thinks close to 90%? Who thinks close to 85%? Who thinks close to 80%? 75? Intuition, please. Just guess, okay? 75? Okay. 70? 65?
How many are there?
7. Yeah. Don't use math. I'm just using intuition. You know, I know math can give you the correct answer. No, 6, 60? 55? 60? Okay. So, okay. Who, other numbers? Who can give you another number? Okay. The actual chance is 0.9 to the power of 7. So it's actually approximately 48%. So it's actually close to only 50%. Okay. And the reason why people think is actually much larger than 50% is because people are using 90% as an anchoring. They're saying, okay, so it's gonna be not too far away from 90. I know it's lower than 90, but let's adjust maybe 20% down or 30% down. I think that's a lot already. But it's actually close to 50%. Okay. The second one is a similar idea. So now, like, people know this, right? So this is the same thing. And if one of these fail, but one of these work, the electric can still go through. Okay. Like, guys, know what I'm talking about, right? Okay. Got it? Okay. So in this case, if one of these things only have a probability of a 1% chance of success, of actually work, and there are totally 10 of them, so n equal 10. What is the probability that these things will work? So each of them has a 1% chance of success. So 0.01, probability is 0.01. And totally 10 of them. What is the probability that the whole thing will work? Who think it's close to 5%? 10%? 20%? What? I mean, this is too slow. Give me some number. What do you think the probability? So you say what? 50? Okay. 50. 1%. Come on, give me some number. 20%. Okay? The actual number is this. So, the whole thing, here I'm using, so this is the chance that you will not succeed. Okay, and let me see. Yeah, this is the probability of a success, right? Yeah. So it's actually 1 minus 1 minus 0.01 to the power of 10, right? This is the probability of all fail. And 1 minus all fail is one of them success, right? And this one is actually less than 10%. Okay. And in fact, most people are guessing around this number, or say 5% or something like that. But it's actually much closer to 10%. Okay. This is also because people are anchoring on the 1% and thinking it's at best double or triple of that number. But it's actually close to 10 times more of that number. And this one, last one about bias resulting from anchoring and adjustment is called overconfidence. Overconfidence actually have a lot of meaning, okay? Another very famous overconfidence biases that people were saying, well, it's not exactly different, but only similar, I would say, is that, for example, if you ask people to judge about their own driving ability, how good are you at driving a car, okay? Most people, and you ask them whether that's above average or below average. And you'll find that more than 50% of the people say they're above average. But that's by definition wrong. Cannot be the case that everybody is above average, right? It must be someone is below average to define average, right? Or you exactly ask median, if people understand what's median, or below 50%. No, more than 50% of people, it's actually around 70% of people will say they are above 50. They are better than 50% of the population in driving. Okay, and that's called overconfidence. It's a very famous phenomenon. This one is a little bit different, but if you ask them to estimate a range, for example, if I ask you to, I don't know if you heard the news, but the future, I'm talking about this future is on the financial market, the future in the financial market for oil in the US has went down to below zero last night. Okay, so if I ask you to predict the oil price of that exact future in 1 month, what will you predict? Okay, that's the question, like you predict a range. I ask you to predict what's the most likely lowest price and most likely highest price, something like that. And even if you ask expert in stock market or in oil, the range that they give you, this is the range, okay? My pencil is out of. So this is the range. Okay. And this range, if you're very confident you will have a small range, right? You'll be very confident you will be in this small range. If you're not confident, you can give it a much wider range. Say the widest range is from minus infinity to plus infinity. Then you must be correct, but you're very not confident, right? So if you give this, and people tend to give a relatively small range, so that what actually happened, like this case, what actually happened is not in the range of prediction. Okay, and the reason why is people are using the current price as an anchor, so it's harder for them to go up a lot and go down a lot. So they predict a sort of a narrow range, but in fact the range could be much wider. Yeah, and I can bet you that before, if you go back to see the news about this future price, before last night, none of the newspaper or expert in this field gonna tell you that the price could go down to even below zero before that. Everybody were surprised. That's exactly what we're talking about here. Okay, because people's estimated range wasn't below zero. They know it's possible to go below zero, but they don't know it's actually gonna happen. Okay? So I finished the most common, 3 common biases. So I'm gonna come back, it's almost 1:50, so I'm gonna come back later and go through the 2 other biases that's very common and talk about why these biases might not be that serious in the real life, and I'll talk about it later.